So now this is the first feature that we're going to look at in terms of the erosion of landforms. So the first feature is the common U-shaped valley, which is caused by glaciation. Unlike streams, which typically create valleys on their own, glaciers will actually take the path of least resistance and follow the path of existing stream valleys. So they will use a path of a previously existing stream valley and create their own valleys, kind of like this time progression was showing you. This is an existing stream valley, and that is the same path that the glacier is going to take. So prior to glaciation, mountain valleys are characteristically narrow and they tend to be V-shaped. So they tend to be V-shaped because the streams will downcut to their base level a little bit faster. So that is how they're going to make the valley. During glaciation, however, the valley is widened and it's deepened by the glacier's erodibility capacity. This is going to make the valley overall have a more U shape than a V shape. So long U-shaped valleys are the resulting features. Many times these long U-shaped valleys are called troughs or glacial troughs, like you're seeing here in the image. And all of the pictures that you have here are of different U-shaped valleys. So this one's very, very clear, not as deep as this other one that you're seeing on top. This one only shows you a little bit of it, but it's still pretty clear that it's a U-shaped valley or trough. The second feature that we have here are hanging valleys. So prior to glaciation, the mouths of tributary streams join the main valley or trunk valley at the elevation of this stream in the valley. So during glaciation, the amount of ice and sediment that is flowing through the main valley can be much larger than the amount that advances through each of the tributary valleys. So this causes the overall, or the valley that contains the trunk glacier, to erode deeper than the smaller valleys are being eroded by their own tributary glaciers, which are again feeding into the main trunk glacier. So this means that after the ice melts, the valleys of tributary glaciers are kind of left standing above the main glacial trough, like the image that we had seen of the glacier retreating in the Greenland's coast. Let me show it to you really fast. So you're left with something like this, where you have the main trunk glacier no longer there, the ice has melted, but you have the remaining tributary valleys on the sides, which again are not cutting nearly as deep as that main glacier had cut. And so those tributary valleys are left hanging, which is why they're termed the hanging valleys. After the ice melts at the hanging valleys, sometimes streams will start flowing through that valley, which can cause really cool waterfalls like the ones that you're seeing on both of these pictures. This one is in Yosemite. I'm not exactly sure where this one is at, but either way, they both look really, really cool. At the head of a glacial valley is a feature called a cirque. So a cirque is going to be a bowl-shaped depression with these very steep walls on 3 sides of it, and it's going to be open on one of those sides, and that side is looking down valley. So this point is going to be a point where the snow accumulation is greatest and where the ice formation used to occur before the ice melted. After the glacier melts, though, it is common to see a lake occupy that cirque space. If this occurs, the lake that is resulting is called the Tarn Lake, and we'll see it in one of the features later in the lecture. So the picture that you have here on the left is not a complete cirque, but rather a 3/4 cirque, if you would. This one is in Banff in Alberta, near Banff. And then the one that you have on the right is a picture of a far cirque over here, and this is in Glacier National Park in Montana. So here we have arêtes, or arêtes, as people here say it. So arêtes are going to be sinuous knife-edge ridges, like the ones that you're seeing in the pictures. These typically are topographic highs that separate two different valley glaciers. So it is easier to visualize them from the image on the left as having that kind of property. One of the valley glaciers used to be here, the other one used to be here. There's a tiny arête here that has now been subdued, but you can sort of tell that this one also split another valley glacier over here. So in this picture, a cirque would be formed right here, pretty much. Here in these other two pictures, you just see the arête for the most part, so the knife-edge looking sinuous ridge separating two valleys, two glacier valleys. Horns are going to be pyramid-like peaks that are connected to arêtes for the most part, but they don't always have to be. They form in much the same way that arêtes are formed by the carving of the glacier on the sides and on the bed of the walls. And so they erode more and more of the bedrock to create those very sharp-looking features. So both of the images on the left are in Glacier National Park of two different, or I guess three different horns. This one right here, this is an arête. This is another arête. This is another arête that are kind of all leaving from the horn's location. This is another horn way in the background. And then this one is another horn that is just above Hidden Lake. In this case, the arêtes have been so subdued that they're no longer looking as if though they were connected to it. The picture on the right here is the picture of the Matterhorn, which is probably the most common or famous horn in the world. The Matterhorn is in Switzerland. I've never been, but again, mean to go. I've heard it's just mesmerizing. So this feature here is called the rocher moutonné, which is a French term, as you can tell. But they form in a particular kind of way. So in many glaciated landscapes, but especially in those that have been modified by ice sheets rather than valley glaciers, the ice that flows will carve these kind of small streamlined hills, like the one you're looking at on the image over here. And they will carve them from any protruding bedrock knob that was originally within the terrain. So, as the image on the left shows, you had a knob or used to have a knob, then the glacier is flowing on top of it and is causing abrasion on one side and plucking on the other. So, they form by the abrasion that is occurring on the side of the hill that points to the direction of the oncoming ice. And then the plucking is going to occur on the side of the hill that points to the direction of the glacier's flow, okay? So the steeper slopes in these features lie in the direction of flow. So they kind of look in that sense like ripple marks do, to obviously a different scale, but you also have the direction of flow, or the direction of flow is being pointed by the steeper part of the feature. So lastly, for these erosional landforms, we have fjords. Fjords are deep, and often times they're going to be steep-sided inlets of the sea that are present in high latitudes where you have mountains that are next to the sea. So they are basically drowned glacial troughs that become submerged as the ice left the valley and as the sea rose following the ice age. So fjords' depths can exceed up to 1,000 meters. So that's just simply amazing. And unlike streams, which basically stop carving at when they reach the base level, glaciers can continue to erode the bedrock below sea level. So this was the case for many of the glaciers, valley glaciers that occupied the current glacial troughs in fjord regions. So, and it happened during the last glacial maximum, for example. So because of this erosion below sea level, the depths at which the fjords have, or the overall depths that fjords have below the sea level is also pretty huge. So that makes them even cooler, I would say. So fjords are in greatest abundance probably in Norway, or that's where we most hear of them. But they're also abundant in British Columbia, in Greenland, in New Zealand, in Chile, and in Alaska, for example. So we have seen the overall capacity and competence of glaciers to erode. Now we're going to go ahead, or to carry things. And you have seen how they are able to erode these things. Now we're going to go ahead and see what are the different deposits that they cause after they have eroded and transported this material. So the deposits that they typically leave have huge implications. In some areas, they will cover all of the bedrock that was once exposed, and they tend to be meters to hundreds or even thousands of meters thick. Maybe not thousands, but several hundreds of meters thick at times. The general effect of glacier deposits is to level the topography, as opposed to the general effect of erosion in valley glaciers, for example. Okay, so again, erosion of glaciers from valley glaciers is going to accentuate the irregularities of the topography. The general effect of erosional efforts from ice sheets is going to be to subdue the topography, and then the general effect of glacier deposits is also going to be to level the topography for the most part. So glacial drift is going to be sediments of glacial origin. It's going to be a basic term for any sediments that come from glaciers. And this glacial drift is going to have different resulting features, all of which are pretty much listed here. Some of them are not necessarily the sediments, but they are related to the deposition effects from glaciers, or they form after the retreat of glaciers, so overall some sort of depositional feature. And we'll go through each of them in the next few slides. So the first thing here, glacial till. So glacial till is material that was deposited directly by the glacier. They're typically sediments that are very poorly sorted, as you're seeing in all the pictures, and then contain all sorts of particle sizes. Many of the pieces within are also scratched and polished, which means that they were a result from being dragged along by the glacier, scratching the bedrock, scratching one another as they were flowing within that glacier movement. So boulders found in the till or that are lying free on the surface are called erratics. And they're called erratics if they are different from the bedrock that is below the area where they're sitting. So that means that the sources of these erratics were areas that were much, much further away from where they are deposited. So sometimes some of these erratics have been transported up to 500 kilometers, and these distances have been measured by different signs of flow that they have been able to locate in the study of glaciers. So erratics can be relatively small, but some of them can be as big as houses, like the one that you're seeing here on the bottom right of the slide.